It's my pleasure to introduce to you our very last speaker for the AutoML for school. And I was saying it's a very awesome speaker. Aleksandra Faust was doing her master's actually at the in computer science University of Illinois. Then was going to the University of New Mexico doing her PhD there, and then was going more to industry, working on self-driving cars already, and then is these days one of the senior staff research scientists working not on reinforcement learning and one of the co-authors of our survey paper on automated reinforcement learning actually. So she really knows a lot of stuff about automated reinforcement learning, and she's here to tell you more about that. So please welcome her.
Thanks so much for inviting. Thanks so much for inviting me, and thanks for bearing with the technical difficulties. And apparently I'm lost up between you guys enjoying the rest of your day. So feel free to stop asking questions. There is material for the slides and so on, but there is enough room for discussion. So several things that we'll go over today is first, I'm curious how many of you are familiar with reinforcement learning, roughly? I'm trying to kind of see hands. So first we'll kind of go a little bit over what reinforcement learning is, why does it need automation, and how we can formulate that problem. And then from there, we'll go and cover common training methods and tools, so kind of know what your tool palette is and so on. And then from there, we'll discuss which parts of the pipeline to automate and what then we'll kind of move into more like from things that we know you should do, here's a recipe, go and do it, to things that are more open-ended research problems and so on. So why AutoML? Let's see how humans learn. This is my daughter interacting with the environment. Basically, we learn through trial and error. We interact with the environment, we try, see what it works, see what it doesn't work, kind of remember, and I mean, over a long period of time, we learn certain skills. And that's the idea behind reinforcement. This is the biological reinforcement. In the artificial intelligence, we have slightly different formulation, but the idea is the same, that anytime we have a system that does something, makes sequential decisions over time, that can be learned as reinforcement learning problem. And the problem pops out in many different applications, from autonomous driving, where the car needs to kind of apply velocity and steering commands continuously, to protein folding, when we're kind of folding the protein and so on over time through a sequence of events. Robotics, there was reinforcement application to the navigating stratospheric balloons, where we're controlling the balloon through the altitude that it's flying, because that's where the winds are, and the winds move the balloon in order to drive it to a certain point, to even nowadays digital assistants that can automate certain parts from kind of our digital experience for us. So since the application space is rich, what is reinforcement learning kind of formally? It's typically defined through Markov decision process, MDP, or hidden partially observable Markov decision process, POM-MDP. And that's a fancy way of saying it's a tuple. And it's a tuple that contains states, as a set of states, so all the states that an agent can be. A is set of all the actions that the agent can take in a given state. P is the probability distribution that says, okay, if I'm in state S and I apply action A, this is the next state I'm going to arrive at. The R is the reward function and that agent receives at any given step. O is the observations. Theta is the set of initial conditions. And rho is the ending conditions, and t trajectories, and gamma is something that's called discount factor. So basically, from there, our goal, or what does it mean to solve FOM MDP, it means to learn a policy by, that's parameterized with some theta, that takes states and either then produces actions or takes a state and action and produces distribution. And that's policy, and out of all policies that we can do, we will search the one that maximizes the expected cumulative discounted reward. So that would be here, this equation. So what does that mean? It means that we want the agent that maximizes good long-term behavior. Just to kind of give you intuition for that, say, okay, you guys are here in a fall school, right? Maybe getting up early this morning was not, well, it's 7 a.m. here, my time. So there is some penalty that I received short term, but over long term, this is a good thing. And even this kind of long-term reward allows us to make long-term decisions, even if it means receiving penalties at a short term. The gamma factors here, it's a scalar that's less than 1 that serves to discount longer-term rewards. So basically, it controls how short-sighted the agent is. So if my big payoff is going to be, I don't know, in 10 years, that's probably worse than if my big payoff is coming in a year. How much pain I'm willing to, to sustain to get a payoff. So typically, we see on the right side here, the loop, how we train the RL, reinforcement learning algorithms, that we have some, let's say, net or policy that we are learning. The agent applies actions in some training environment, interacts with the environment, collects some data, receives back new observations as a result of the actions taken and the reward, and that kind of updates, and that's the loop. All right, so typically, what are the components of reinforcement learning? And if you're not familiar, you might kind of hear these terms, so here's kind of a very brief overview of what they are. Something that's called value functions. And value functions will tell you what is my expected return in the current state, if I'm acting within respect to a certain policy or within the optimal policy. The state action function, it's a Q function, what is the potential payoff from my current state if I take an action A? Subtle difference. The reason it's separated is for basically Q is easier to learn than V function, because V function fully depends on the action, on the policy that we're working on, whereas Q, we're doing the next action, and then after that is dependent on the policy. So these two are the two big ones, and then as we're kind of learning these two functions, there is the exploration versus exploitation trade-off. So anytime that the agent is acting, it's acting within some policy. The question is, do we want to exploit that policy, or do we want to explore, do something else, and then maybe gather better data, but then at the risk of potentially degrading the performance? And how to control this exploration exploitation trade-off is a big question in reinforcement learning. So in terms of the pieces here, we have the reward, we have the state transition function that learns the model. So if we're doing model-based RL, we'll have model. Then from there, we can either learn Q function, V function, and if we have either one of these, we can learn the policy pi. We can learn directly policy pi, we can learn Q function, and then derive pi, or learn model, and so on. So the different algorithms do approach it differently. So if we're learning model, that's called model-based. If we're learning value functions, either Q or V, That's value iteration, reinforcement learning. If we're going after policy, it's either policy search or policy iteration. And then if we're learning two of them, it's actor critic methods. Just terminology. All right, so don't expect this to be memorized, but just to kind of give you an idea of the taxonomy of the reinforcement learning algorithms that have been developed in the last, I don't know, let's say 5 years or so. There are model-free and model-based algorithms. We mentioned model-based are learning the model and then going from there, and then model-free don't skip the model, either go directly for policy optimization or Q-learning, which is the value-based models, and so on. Terms to kind of know is off-policy and non-policy. Off-policy means that agent, I mentioned exploration, right? So when the agent goes in and collects the data, is it using the same policy that's learning? If it does, that's called on-policy learning. So both policy and the explorations are kind of used on the same, and some algorithms like PPO here is on policy, A to C, and so on. Off policy means that agent is learning certain policy, but it's using a different one, maybe slightly perturbed one that it's learning to collect the data. And algorithms that are examples of that are DQN, DDPG, and so on. Offline RL means that agent is skipping this loop where it updates the policy, gathers the data, and updates the policy again, rather kind of tries to reduce it down to the supervised learning. So it has a data set and does one-shot update of the policy. The other distinction to make with the algorithms is, are there discrete or continuous actions? Discrete actions means that agent is basically choosing a categorical, I want go left, go right, up and down, enter this text field or whatnot, whereas continuous action space is, you shall go by velocity, I don't know, 2 meters per second or something like that. And the reason to differentiate between the two is when we're getting to the policy. For the discrete actions, we can just do argmax. We need to do argmax. So in the discrete cases, that argmax is basically just selection out of the list. Whereas in continuous actions, this argmax becomes an optimization problem over function that we generally don't know. So we need to either learn that or figure out some other way to get the maximum action. And then some algorithms can do both. So PPO can, for example, do both discrete and continuous actions. All right, any questions here? No, we can move on. All right, so what's the big deal with RL and why is it so hard? How is it different from supervised learning? There are many reasons, but let's kind of highlight 3. It's a combination of 3 factors. First off, supervised learning has a different formulation. Reinforcement learning solves POM-MDP, where there is no one loss function or one signal classification or regression at the end, but rather we're optimizing over this sum of the rewards that were occurring, that we're expecting to occur during the trajectory. Second reason, and we'll kind of go from there, is that application space. So whereas supervised learning produces recommendation or produces classification, and then user can decide what they want to do, reinforcement learning solves control and planning problems, which means that it puts the model in charge of whatever the device is. And these can be high consequence systems, such as self-driving cars, right? The decisions that the system is making are alerting or changing the world, right, around it, and they can cause damage and so on. And then there is the dynamics between the closed loop training and the evaluation. We'll kind of go more over that, but that closed loop is not present in a supervised learning. It complicates things. So closed loop training, the fact that we have an agent that, or the network that we're training, then performs action, collects the data, receives the observation, it causes the distributional shift in the data. Every training iteration gathers the data from the changed environment, because agent, when it makes step in the environment, it changed the environment. If nothing else, the agent changed the location from the last node. So there is this kind of continual shift in the distribution over time. And that kind of causes some problems. So one of the ways to solve that is we make the basically stack more complex. So instead of having training agent, we have training agent, training network, and then we have a set of actors, what they're called like the neural nets or these off-policy networks that stabilize training. So we're having the network that we're training, and then these actors are frozen for time being. They go collect the data, and instead of going directly, there is this database where we call replay buffer that they store the data, and then training agent basically gets every once in a while new batch of data from the replay buffer, updates the actors, but that doesn't happen at every single step. And that stabilizes the learning at the cost of making stack more complex and so on. And every time the stack is more complex, you should hear more hyperparameters, which means more things to tune, which kind of brings us to here. But here is a good example of the distributional shift of the evaluation time. So in this case, we're asking robot to go to the sink, and it observes basically with the LiDAR, the depth, and it reacts with the action. So in the second round, the road was blocked. It needs to kind of find another way and goes around and basically needs to adapt to the things that they're going. So this type of things are very hard, and this is not this is not staged. The policies need to kind of adapt to these type of changes at the runtime in the environment, whether they're coming from the external factors like people walking in or so on, to basically people reacting to the robot, or robot kind of changes its locations. This is, by the way, AutoML trained policies, so we'll talk a bit more about that later. So because of the application space, another difference in between supervised learning and reinforcement learning is that once we have trained policy, we need to kind of put it on device, whether it's a robot or whatnot, where it needs to make sequential decision making. So this is the case where bigger is not always better. Basically, the common wisdom says the larger the model capacity is, the better agent's gonna do, more accuracy and whatnot. While that might be the case, in these environments where things are changing, right? Highly dynamic environments, the bigger the model capacity, the inference time takes longer, right? What it means is that as my inference time takes longer, the world around me is changing, so my decision is becoming more stale. And the certainty and the safety of that decision is diminishing over time. These are my hand-drawn lines that they're not measured and so on, but basically it shows this tag and pull in two different directions, that there might be a sweet spot somewhere with the smaller models that can actually make fast decisions and react fast in a highly dynamic environment. And again, guess what? We're solving this through trial and error. So finally, last reason it's worth mentioning here, why how reinforcement learning is different than supervised learning is, well, we're using function approximators to represent the policy, right? The moment we get into from the fixed small number of states and number of actions, we need to start relying on function approximation. So my policy or my value function and so on, neural nets and so on. And there are nowhere in this POM MDP formulation that it mentions function approximators. Right, so what does that mean? It means we're solving problem approximately, which means we're causing errors, and basically the mathematical formulations and the mechanisms that we have around convergence basically start to fall apart. And again, brings us into this trial and error state. We're experimenting with different neural network architectures and all kinds of other settings to see what it works. Similar to that, normally, again, these are real systems that we're hopefully want to work with and so on. They interact in real world with real world, so training them on real data is probably not possible, right? We don't want robot like my daughter going in and, and boinking onto things and people while it's learning. So we end up training in simulation, and there's a question of how do we design simulation environment and simulator, and then how do we deal with what's called sim to real gap. So if the simulator is simpler, which always is, and then we plop that policy on a robot or real system, there is the gap between the two. So how do we address it? And that makes the stack, I guess, more complicated. So I just mentioned this, that because it can cause damage and so on, it needs to work in structured environments, and we need to design the training environment carefully such that it can generalize to the real cases. All right, so to summarize here on how is reinforcement learning different from supervised learning and what makes it difficult, is that at the intersection of the closed loop training and POM MDP design, we need to think about model latency. Between the closed loop training and the application space, safety and dealing with the distributional shift is important, and it generally kind of being done through different algorithmic design changes that kind of lead to the training stability, handling generalization and uncertainty, and so on. And then between the applications and POM MDP design, at the core of that problem is the simulator design, and then function approximation and the right function approximations touch everything. So there's a lot more bells and whistles and knobs to tune in reinforcement learning than in supervised learning. Any questions here? All right, I'll move on. So what's the reality of training reinforcement learning agents? We started with the stack, right? That we have the training algorithm that interacts with the training algorithm that interacts with the training environment, collects the data with a bunch of tuning here, and then in the other day we go in real environment. And how do we know that we do that well? Well, there is an engineer, and this was large part of my PhD, tuning different rewards, tuning different things, and then make the decision what to change, train, go again, and so on. And it's really human in the loop, sequential decision-making problem, because this person is making all the decisions based on the prior data and whatnot, and recommending the next parameters to try. And if that's really sequential decision-making process, then we should probably learn it. So what are the hyperparameters here that we're learning? So we kind of can divide it into reinforcement learning focused components. This would be the algorithm and neural network architecture and so on. There are questions around task definition. If I'm faced with a problem, what is the reward I should give it? Unless I'm working on an RL benchmark that already has rewards given, in any real problem, rewards are not given. So one needs to design them. Then there are questions around how do we design the agent itself? What are observations? What is the simulator? What are the actions that the agent need to perform? And then in what environments to train the agent, kind of going towards curriculum. So there's lots of things to do in there. And as I mentioned, since it's repeated decision-making process, we can replace it with a model, and we call that AutoML. It's kind of broad scheme. Thanks. So what is really AutoML problem? Now we have two parameters, right? We have our objective function where theta is our policy or whatever is that we're kind of learning as part of the POM MDP solution. And then the other parameter is the hyperparameters. So our basically training objective is to or AutoML objective is to maximize this other parameter such that for the optimal theta that produces the policy. And we can kind of put it as an inner loop problem and the outer loop problem, and it's a bi-level optimization problem. So the inner loop learns theta, the outer loop learns psi, the parameters. So then we can kind of learn the internal, every once in a while update the policy. We can do entire learning of the policy and then span a whole new agent, try different hyperparameters and so on. And there are many ways to do this, but that's roughly the space. What are types of the hyperparameters? Just by type, they can be categorical. This would be things like, I don't know, discrete numbers. Buffer size is usually at the orders of magnitude powers of 2. So 128, 248, 124, and so on. It can be a vector, so continuous values. It can be a symbolic, such as graph representation, or it can be parameterized functions, well, neural nets for all the purposes. And we're going to see that as a high parameter regime. So it is still continuous like a vector, but these are high parameter regimes with millions of weights to learn. And to kind of solve the whole problem, this is a combination of all of them. Low parameter regime for the categorical, and then symbolic is the high parameter regime. So to represent the graphs, it's still categorical, but there are lots of edges and types and so on that one needs to learn. What's interesting also is that big question that we don't know is how many of these hyperparameters are codependent non-linearly. And largely we don't know that. that makes things more complicated. So next kind of thing to think about is, as I'm training my agent, right? And the agent is, I'm talking about the inner loop. The inner loop is kind of has several iterations. So there's step 1, step 100, step 10,000 and whatnot, and it can go up to millions. To train a single agent to the right skill level. Is the hyperparameter holding, if I pick one hyperparameter, is this hyperparameter fixed for the duration of the entire training loop, or does it change over time? Here is an example here of a function that kind of changes over time. So the hyperparameter, the max, changes from different steps. And if we average out the best performance, it's not gonna probably be the best. So this is what we called stationary. If the hyperparameters remains the same throughout the training of the agent, seed and discount factors tend to be these. Non-stationary, we know that exploration rate, which basically says, okay, how often should the agent go off the suboptimal of the what's best policy that it knows so far, and learning rate should change or duration of the training. For the other parameters, such as neural network architecture, discount factor, maybe there is some work kind of looking in this space as well, replay buffer size, how the sampling policy, like which data we sample out of the replay buffer, loss functions and so on. We just don't know whether they are stationary or non-stationary. All right, so this is a long way to say that AutoRL problem, as we kind of define it as this two-loop problem, is expensive. Just an example, this is for the outer loop. Simple soft actor critic algorithm, take it out of the OpenAI stable baselines. It's governed by 28 hyperparameters, which do not include neural network architecture. They don't include loss function or the loss function. It's kind of part of the algorithm, right? And they don't say anything about the environment design. This is a huge search space. And then we combine that with reinforcement learning, which requires often millions of samples and days for training. And if we're talking real applications, we're even talking weeks of training for a single loop. And the cost is multiplicative. There are some works now on trying to not start from scratch training, so kind of having this inner loop, outer loop happening more often potentially, and so on. That's kind of in works. However, the cost remains very expensive. Any questions here? All right. All right, so then let's kind of recap what are design considerations that in this inner outer loop. The hyperparameters is everything that's not specified in POM-MDP. They can be categorical, symbolic, continuous, or differentiable. It can be stationary and non-stationary, and there are some codependencies between the hyperparameters, which we largely don't know what they are. I'll kind of say where we do kind of later on in the talk. And second kind of take home point here is that evaluations are very expensive. In this case, the evaluation is training the RL agent. We're searching in a large space and the evaluations are long. Hours, days, heck, weeks. All right, so now on next part, I want to kind of just go briefly over what are the training methods, what are different tools that we have at our disposal for the outer loop. Now we're going to kind of focus on the outer loop. And then after that, we're going to talk about what are, like, the problem is huge, so how we are currently divvying it up and what are the pieces that we're learning and so on. Okay. So one kind of very simple is doing a hyperparameter search. And the reason I have this slide, because I've seen it so many times, and I want to kind of put in a tutorial that anytime. I've seen so many times people do a grid search in multidimensional search spaces, and please don't do it. It's the worst thing you can do. There are better methods and whatnot, but if nothing else, use a random search. The reason is that once you're in a multidimensional space, even with two dimensions here, doing a grid search gives you less information per dimension on the function than random search. So random search, if you kind of have, I don't know, n by n, you're gonna get n data points on one axis and data points on the other axis. If you're doing random search, you're gonna get n square data points on one axis and n square data points on the other one, and that will allow you easier and quicker way to estimate the functions per dimension that you're looking at. So please don't do grid search, period. It's my pet peeve. So second useful tool are evolutionary methods. And I'm sure you're familiar, so I'll just kind of go briefly. The idea is here to initialize population. Then we calculate the fitness function, basically it's given some objective function. We select some survivors here. Maybe these two are not performing as well and they're being discarded. And then there are two ways to kind of create a new population members, either mutating existing ones or combining two existing population members into one. Then we check the stop criteria and we have the new population that we then calculate the fitness and then go on and select survivors and so on. The second kind of, or I guess third now, tools that are useful for hyperparameter optimization and these other loop and multi-arm bandits. And you can kind of think of it as POM MDP light. It's basically a stateless action selection. So here is the kind of the hierarchy of the we have the unknown environment observations. This is the goal of the reinforcement learning. There is some hidden state there, and then the bandit problem is just, okay, I'm going to receive the reward, I'm going to give you action, and the bandit is basically, okay, pick 1, 2, or 3 option, and so on. It's much faster to train, and so on, and it's a very practical tool for selecting hyperparameters. Bayesian optimization, also very handy tool, very quickly. Sample the function, put a regressor through it, usually Gaussian process, that estimates the uncertainty of the objective function based on the previous data. Then we create an acquisition function from the regressor, which represents the explore and exploit trade-off. And then we find the argmax of the acquisition function that's used as an X trial to collect the data, and then we kind of repeat the process over and over. For the optimization methods, when we're kind of in differential space and so on, MAML or model agnostic meta learning is also very useful algorithm, and it's learning, the algorithm for meta learning trains the model's parameters such that a small number of gradient updates will lead to the fast learning on a new task. So basically, we're trying to find a gradient that goes in and can adapt through kind of sampling small number of trajectories that can go in the right direction. And then if we're kind of faced with a particular task, theta 1, theta 2, or theta 3, then you can basically do a few shots transfer to the new tasks. And then lastly, there has been emergence of population-based methods. The idea here is that they optimize both population of models and their hyperparameters. And this kind of falls into learning non-stationary parameters. So maybe certain agents are having certain parameters, right? They're maybe improving their performance over time. The blue agent at the bottom, then at certain times, like, well, that's not quite working. It may borrow or change, swap the hyperparameters with another agent for population, and then continue training with these hyperparameters and so on. And so from that perspective, it's really non-stationary. The parameters are being changed on the fly. All right, any questions here? Hope you guys are awake. All right, you muted. So let's talk about what to learn then. In a broad kind of strokes, mentioned earlier, there are reinforcement learning focused components. This would be hyperparameters, neural network architecture, search, learning algorithms, and so on. Then we have the learning the rewards and agent-based settings and the environment-based learning. But first, we'll kind of go a little bit through the tools for hyperparameter optimization. So there are basically three types of tools that are available in this space, or I guess different packages. So service host algorithms, services host algorithms in a central server, and these include things like open source Vizier and OpenBox, and they're generally more flexible and scalable, but at the cost of additional engineering and complexity. Now, frameworks execute the entire optimization themselves, and while they're convenient and automate everything, they also require knowledge of the entire evaluation pipeline. And these include things like AX and HB bandits there. And then lastly, we have the libraries that implement black box optimization algorithms. And they offer the most freedom because it's a library, but usually lack the scalability features and are limited to one machine. And things like that are PyGlove and Blowtorch. So deeper dive on open source Vizier service. This is kind of one of the example of the service agents or the service tools. It is set up as a client server protocol, and it allows multiple clients to work on the same task. So this can be useful in the batch settings and so on. It also supports many types of the black box optimization. So the Pythia server here kind of hosts the algorithm, and then we have a number of clients that go and execute evaluations. So in this context, this might be running different RL algorithms and so on, collect the data that goes in the data store, and then from the Pythia server, the black box optimizer recommends the next parameter. And this can be all parallelized. So here is like a deeper dive. This is open source. There's the link here. So how would one set up the Vizier? There is the example here with the dopamine where one can import RL benchmarks, and there's the Vizier and the client. So now to set up the experiment, we just do RL benchmarks, this Atari which game, and which agent. This would be basically the algorithm we're training. The problem statement will contain things like which hyperparameters to learn, what is their type, what is their lower range, what is their higher range for the search space. And then we set up a study that says, okay, this is my problem statement. So which hyperparameters to learn, what is the algorithm, the black box algorithm, in this case, Gaussian process bandit. And we create or load the study where we're linking it to, and off we go. And then how many clients we want to run. We can say, okay, suggestions, client gets suggestion, what is the parameter to try. We run evaluation. Evaluation is the inner loop here for the RL agent, and completed trials gives the data back on how well that agent performed, and then we kind of continue that for the number of desired trials. So it's fairly simple to set up. All right, so now I can kind of move on and talk about the methods for neural network architecture learning. So in reinforcement learning architecture matters, another window popped up. So in the RL architecture matter greatly for inference speed, generalization, and sample complexity, in adaptation as well. So improving these aspects contributes greatly to the deploying RL in real world, such as for robotics, right, or any of the other tasks that we have before. However, to perform the neural network architecture search in RL, we need to discuss some of the methods. So main focus will be on the efficient methods, rather than the original trial by error formulation, because it's too slow and expensive to be used commonly. And this is because, for example, as I mentioned, like even in supervised learning, it takes more than 2,000 GPU days to perform neural network architecture search on CIFAR 10. And if you kind of just imagine doing that over in multiply thousands of times for get PRL, it becomes very expensive. And we also have complication that reinforcement learning trials are generally noisy because of this non-stationarity, right? And the sample complexity can even be orders of magnitude more. So the question is now, what are the efficient methods? So in the low parameter regime, and we're kind of thinking low parameter here means less than 10,000 weights. So that's the first class algorithms. They're intended to be used for policies that have no more than about 10,000 weights. And they're based on the idea that optimizing architecture and weights simultaneously. The many non-differentiable and evolutionary algorithms come to mind here, such as neat or regularized evolution. We can kind of basically pick and choose the edges and so on in the neural network architectures, as well as the hybrid methods such as recent ENAS. They're used for lightweight environments such as these are environments, Carpal and Udracode. But once you start getting them to the more serious environments, they really have a hard time scaling when there are too many parameters. So modern reinforcement learning algorithms are now they're not fully at large language model scales, but seeing tens of millions parameters is not unusual. So that kind of brings us to the high parameter regime, where gradients are almost always necessary to train the weights. So one method that we found that worked well, and it's very non-invasive, is differentiable architecture search, or DARTS, and that ends up working in the RL. We found that we can simply replace a network component with Dart SuperNet in pipelines for algorithms such as PPO, DQN, and soft acrocritic. And you can kind of see here from the code snippet, basically just replace base policies making Impala CNN network to Dart's policies, Dart's Impala CNN. It's open sourced. It's literally one line of code. And the method then learns both the weights and the pruning the weights at the same time. So this led to the search capabilities, which we applied to ProgGen and VM control suites. Question here is, can it really scale to more serious problems that are less benchmarking in real world? And I guess that's one of the open questions. That kind of brings us to the open questions. So for the other methods in the high parameter regime, so far many of the methods from the supervised learning have been untested, and that's exciting. So in the black box optimization setting, for example, consisting of methods such as regularized evolution and Bayesian optimization, one issue that will need to be addressed is the inherent noise in the RL. That's really kind of the show-stopping case for these methods. The other weight sharing methods, such as efficient NAS or ENAS, will need to address simplicity in implementing such methods in the distributed RL settings. And again, that's an open problem. And then lastly, other methods for addressing high parameter regimes, such as the classic hyperneat, may need to be modified in order to scale to modern deep learning settings. Lots of work that can be done here, and that can really make a big difference. So next, let's talk about the loss functions. So the idea here is that the loss function that we're learning in the inner loop is a parameterized object. And there are two general lines of work in this case. We can represent loss function as gradient problem, so it's a neural loss, or a symbolic function. Search space here is large, and that's an understatement. The loss function here is the entire algorithm, right? Or can be just a loss function, and it can scale to 10 to the power of 100. So careful design and pruning and optimization and all these painstaking methods are really key to succeeding. So here are some examples of the work that has been done. Treating the neural loss functions as, or solving it with evolutionary algorithms as an example. The premise here is that agents should learn the objective depending on the context. So this is done in Mujako environments where they're randomized, and basically loss function here to define the temporal convolution for the loss function, and as the network kind of looks in the current context what the agent is doing and so on, it adapts to the environment and the data that it had seen. It leads to faster training and better generalization to the alto distribution data. So that would be the red curve here. Again, only done in toy environments. So next set of methods is using the gradient descent as a neural loss function. So one example is MetaGen RL. Each agent learns local update rules, and then they are being combined into a single meta objective. The kind of idea that each one of them is using localized knowledge, and that's showing promising results. In the other example that O and L did is the agent is learning, or the loss function, you have two types of networks. One is learning what to predict, and then the other one is learning how to predict. And it generalized from toy grid environments to Atari games. Again, not tested on real world problems and so on, still contained very much in research. The main kind of caveat with the gradient-based methods is that they require Jacobian vector for computation, which nowadays in libraries such as JAX or TensorFlow or PyTorch are readily available. So it remains to be seen. There's some promising sign that there is a cross-domain generalization here. Stay tuned, or do research, try it, even better. See how well it scales to more serious applications. So then there is a class of algorithms that does a symbolic loss functions. In this case, basically, the loss function is defined with a domain-specific language. The downside is one needs to design that domain-specific language. Good positive is that these loss functions now are interpretable, and they're math functions and whatnot, so we can use the same tool set to control them. So two examples. One is the DSL is using domain-specific language to represent the curiosity module, which is trained then with the regressor. So the curiosity module provides intrinsic rewards, which are then added to the loss function that can be optimized with a standard PPO algorithm. The search space is about 52,000 programs that combine neural networks with other building blocks such as buffers, nearest neighbors modules, and so on, kind of going into the larger picture. And in general, it's to the variety of the domains. So in the other example, and we'll kind of take a deeper dive on this, we proposed domain-specific language to represent entire loss function as directed as acyclic graphs, and used kind of number of tricks here. But this is the first time that we have a large database of loss functions and how they perform on, and how they perform, right? And there is kind of interesting. We're not surprised that lots of them are not doing anything. We're not surprised that lots of them are doing well because that's what we're optimizing for. But what's surprising is that there are clusters of areas here only with the 20,000 algorithms that we only have 100 or 200 different values. And that's surprising. So kind of just briefly here, the idea is that we're learning the algorithms or the loss functions. And basically the idea is the whole algorithm or the loss function is a hyperparameter and kind of maps to a certain objective. And we're going to go now more into the representation and search space design and do a deeper dive on the methods and tricks and do a code and collab example. So the algorithm here is basically a computational graph. This is one that represents the QN function. And then how do we turn this into hyperparameter and vice versa? So each graph can be viewed as a sequence of categorical hyperparameters, one for each intermediate node. So we always have fixed inputs. We know that it's a state. It's the parameter that we're doing, the next state, right, and the next parameter that comes out. The Q function, and then the output is a scalar. So more specifically for each of the intermediate nodes then, and for the output node, we use kind of operators of plus, minus, and so on, and define which are the previous nodes as inputs. And then for the output node, we specify what are the previous nodes that it gets into that. So this encoding and decoding logic is necessary for mapping, going back and forth between hyperparameters and graphs. So here are the search space that we have. So we have operations such as add, subtract, max, min, and so on. Different input types. So add kind of takes two parameters. List takes, or max list takes a list of real values, and so on. And then the output is a scalar or so on. So it kind of covers the typical operators and so on that are seen in the value-based RL algorithms. And then in practice, we need to set the maximum size for the algorithm, and about 20 nodes seem to work well. So then our optimization objective, we need to do that and then plug in our favorite hyperparameter tuning algorithm. So optimization objective here is the sum of normalized returns on the meta training environments. We use the regularized evolution, and then it's really necessary to do distributed training. So for this work, we basically use about 300 CPUs for 3 days, and we evaluate about 20,000 candidate functions. So there are a couple of tricks that also need to be done, is that when we're training and evaluating, so this is the inner loop, we have a loss function, candidate loss function, we want to see how well it's doing. So we first have a hurdle environment, it's a cart poll. It can train in minutes, and if you can't learn cart poll, you have no business in continuing and doing more complicated training of the environment. So that's our hurdle. If you can't pass that, we're not continuing. If it passes hurdle environment and goes to the training, kind of more complicated training environment. So the second kind of big trick is that we actually use hashing to approximate the functional equivalence and caching. So if we compute that the graph is same and we already have a value for it, we're not going to recompute it. So what are the algorithms that were discovered? We actually discovered regularized DQN, which is very interesting because it's very similar to the constant of CQL, which is kind of state-of-the-art in offline RL learning algorithm. You can kind of see the purple line comparing to the baselines, including the CQL. We see that it is it generalizes to other mazes, and DQN agent is really not exploring here much in this maze, where DQN reg does pretty good. So we're thinking that regularizing Q early on in the training does kind of encourage more exploration. It also, even though it's not trained on the visual environments, it transfers to Atari games, and it outperforms the state-of-the-art in Atari games, in the 4 Atari games that we tried. And it's interesting, it's consistently discovered within the constant. All right, so what's gonna do, this is the tutorial, do a little bit of the deeper dive, how to set it up in PyGlove. And this is open source as well. So there is this one-off parameter in PyGlove. This is a single process training. It's fully open sourced, and it's built on 2 libraries, PyGlove and AutoML library from Brain. And Acme is RL library from DeepMind. So first, let's define our search space. We recall that we want to represent graphs of fixed length, and the vertices are topologically sorted. So each operation has many choices, and this translates naturally to PyGlove's primitives, list of PG one-offs objects. So list means that I can kind of go append. One-off, it means it's going to pick one of them, and then one of what? This is the product input ops, where I have my combination of inputs, existing ops, I operators, and freeze ops. So that's basically the graph. Lots of them are not going to be valid at all. So this is kind of where caching and simple synthetic search do help. Second, we need to define our search method. And here's the snippet that uses and sets up the regularized evolution. So there is the evolution methods, reproduction, do the random tournament style with what is the size of the population, what is the seed, how to select we're selecting one top performer based on the graph mutator, and then we're initializing the population with the graph generator and the population size, and we're updating based on the list such that the population size is kind of bigger than what's in the cache. And there is a whole demo collab or Juniper network notebook that you can kind of see. So the main training loop, basically we just loop through decoded hyperparameters. We get the evaluation result through sampling out of the search space based on the generator and whatever the flags are. And just kind of this toy example going over 100 trials, we see that we're actually starting to pick up some signal. All right, so for the algorithms, basically the main takeaway is that we really need to be careful about designing, pruning, and optimization. There are some signs about generalization across domains in discrete action spaces, and policy gradient and actor critics are really more challenging. So next kind of topic is rewards. And this comes with the idea that in real world problems, rewards are not known. And there's something that's called sparse rewards. Then we often have the reward at the end of the episode, whether the task is completed or it's not. And in order for agent to go and get that feedback, it needs to do a lot of exploration, and that becomes very quickly intractable. So then people kind of design these intrinsic rewards, which are basically are intended to provide more dense feedback to the agent. One way you can kind of think of it is if you're completing a task, the intrinsic reward gives you the feedback as how well you're doing along the way. So here's an example from a robot. This is, remember the first video that I showed earlier? The only difference between this robot and this policy is the parameterization of the reward, the intrinsic reward. So what basically the better reward kind of produces more smooth and more efficient behaviors. Yeah, as I mentioned, like they're difficult to design and so on. So in this space, there is work that does reward shaping. It's also known as reward shaping for policy gradients. So inner loop here is the gradient descent over sum of both intrinsic and extrinsic rewards. And the outer loop is the update of the intrinsic reward to maximize the extrinsic reward. And we see improved performance in more difficult environments such as humanoid and so on. So in the other work that we did, this is actually our work, that Chang and did is, we start with the idea that we might have a good intuition what features might be about the intrinsic reward, and we kind of use that. And then the reinforcement learning uses feature-based intrinsic reward, and the outer loop is evolutionary algorithm or Bayesian optimization that basically goes and runs many trials to maximize the extrinsic reward. We'll kind of talk more about that a bit later. And then there are methods like byparse, where inner loop is the PPO, and the outer loop for the reward uses defined reward shaping function with meta learning. One kind of takeaway is that reward shaping and learning these intrinsic rewards help with more complex tasks. It's less important which method you use. What's important is if you have a difficult problem, that's the first thing to try, rather than kind of doing other hyperparameters and so on. So learning the intrinsic rewards that completes the task, basically the idea here is, and this is the robot example I mentioned, but we've done it in the other environments as well. So we wanted robot there to go to the goal. It was sync in that case. So you have the coordinate, you can kind of say, hey, this is the task you're wanting to complete. So it's very simple, go there and do that. In Mojako environments, might be things like run as fast as possible, maximize the speed, and so on. And then the rewards here might be, well, it depends on what's the speed of the robot, what's the distance to the nearest obstacle, how far we are from the goal, and so on. but how to combine that reward is really not clear. So that's a parameterization of the reward. And we start with a population of agents. We're running 100 at a time. Each starts with a mutated reward, they're randomly initialized. We evaluate them against the task objective, which is we reached the goal or we didn't reach the goal. And then we get a mutator that basically recommends the next reward and spawns a new agent. And then again, we select a policy and a reward that makes learning tractable. So single trial, in this case, in the robot was equivalent to about 12 days of training. It was 12 hours wall time a few years back and took about 1,000 trials or equivalent of 32 years of training experience or 5 days wall time to get actually to the video that I showed earlier. So it's not cheap. And here is an example. This is the training environment that we're using, very, very simple, right? And then it does zero-shot transfer. We don't need to do anything on the robot. It works on a variety of the robots and generalized to many environments. So I didn't mention that we kind of then did the benchmarks on the other environments, and we kind of find that it does help with more complex tasks. We also found that if you have a fixed training budget, you're more likely to find better policy by tuning the rewards on a complex task than either hyperparameters such as learning rate or discount and so on. And then surprisingly, we found that there is a codependency between RL algorithm and intrinsic reward. So even in these environments like which, of course, I don't know how well you're familiar with them, the reward is given, it already has the parameters. So if I use that as my training objective, and then my intrinsic reward becomes that same reward, but with learning the parameters, so basically reparameterizing the reward, the right parameterization depends on the algorithm. So we're using soft actor critic or PPO or DTPG. Each one of them has different reward that's going to still complete the task that needs to be done. They're better than just using the native one. And we're speculating this because that intrinsic reward helps with the path in training and kind of provides more efficient path. Anyway. All right, so then kind of briefly, let's kind of talk about the environment-based training. Here we have things that are action space, observations and dynamics, things that we need to kind of design if we're designing agents from scratch. So on the action representation, there is work that presented an extension of idea by conditioning the amount of repetition. So there was work that kind of looks in the reward space, how many times we repeat certain actions. So things like, okay, make 20 steps. So instead of saying step, say 12x steps. And then kind of expanding on that idea, condition the amount of repetition on the predicated action itself. They showed it's possible to combine actions into suitable macro actions by defining sub-goals to be reached in the environment. And this is done by partitioning the transition graph, and both result. It shows significant improvements in the speed of the training. In terms of the observations, there has been some work proposing the bandits to select image transformations and basically provides more robust training, things like crop, rotate, and flip, and applying it to the observations, and that actually got state-of-the-art on the ProgGen environments. And even though I'm not technically AutoRL, but it's worth mentioning the world models that are basically learning the vision and memory and learning the model that then can be used for model-based training. So then there is an emerging, we're doing good this time. There is an emerging kind of now trend on the curriculum learning where orders of task environments, the question here is how to order task environments to be presented on the agent to speed up the training. And some notable work, he's doing combinatorial, multi-objective evolution, or learning progress based on the multitask curriculum, or recently paired to use the constrained environment and generation that kind of takes the feedback from the agents under training to propose the next steps. It is sensitive to the learning methods though, although it helps with the generalization. It's a very active area of current research. And then we're kind of talking about learning the rewards, learning loss functions, learning pieces, but then there are some promising methods also looking at a combination of the components. Learning things like rewards, neural network architectures, and so on for the RNA, or learning combined neural network architecture and accelerator design together. These are kind of promising, again, area of active research. All right, so what do we know? We know to learn hyperparameters. And by hyperparameters, I mean these like simple scalar ones like discount factor, learning rate, seed, and whatnot. We do know that learning intrinsic rewards for complex problems is the thing to do. And there is a codependency with the RL algorithm. We do know that using curriculum for complex problems does help. And it's very sensitive to task. There's like lots of work that still needs to be done. It's not fully out of the box. We also know that loss function learning has a promising generalization results in discrete action space, and it still requires careful design, pruning, and optimizations. Now, what the things that we don't know, that's active area of research, very little work in neural network architecture search. I think this is like really, if you're looking for PhD thesis, that's a good one. There is very little work in agent learning. How do we design agents that actually generalize and so on? So there are observations, interactions, and whatnot. We don't know what are important components to learn. Is it more important to do neural network architecture or the word, combination of the two, and so on? We don't know what hyperparameters are stationary and what are non-stationary. Learning many components is the thing to do. However, it's currently not very tractable. So finding efficient methods how to do that is paramount. And we don't know what are the best learning methods for each component, whether kind of go with Bayesian optimization or evolution and whatnot. So what are some open problems? We need more theoretical understanding around the hyperparameters codependencies and what methods are appropriate for what. We need more practical benchmarks. We don't have them. The non-trivial RL problem and the tractable outer loop and the metrics. Like the reward is just not enough. Nature and versus nurture trade-off. What I mean by this is that nurture is the data that's being fed to the agent. So what environment is being trained on, what data it kind of collects, versus nature would be your hyperparameters, things that are like observation space and everything else that we know. At which point do we change what data is being presented versus what neural network architecture we do, or what the codependencies between the two? And then last point is the integrative methods. Things that, such as population-based training, multi-generational evolution, where we have many agents and maybe some they're exchanging parameters, learning from each other, and so on. And maybe that's one way to kind of tackle the complexity. Okay, so to summarize quickly, and we'll have some time for questions. There is a fundamental difference between reinforcement learning and supervised learning. There are a lot more knobs and interdependencies. The stability of training and generalization to do to the non-stationarity is really key and how to deal with the auto distribution methods. The computational cost of AutoRL is the cost of AutoML times cost of RL. So you have two expensive things, and things kind of get really complicated. The hyperparameters kind of think of in terms of numerical, symbolic, neural, and stationary versus non-stationary. And then learn parts of the system. What are really the parts, like the standard, like the scalar, hyperparameters, neural network architecture, loss, functions, rewards, agent environment components. And then for future work, really looking into the codependencies, non-stationarity of the hyperparameters, and scaling up. And just to see what 10 years of AutoRL training does, joint curriculum and non-stationary hyperparameter fitting. This was my daughter 10 years ago. This is my daughter as a few months ago. It does work over a long period of time. And I want to thank King J and John, JD and Jack for kind of helping out with the slides. And there was a survey paper that Marius had mentioned that lots of us are on it. And thank you.
So, are there any questions? Please come to the front and best. Yeah, but that's there. And then also,
okay. Hi. So thanks first of all for the nice presentation. I wanted to ask for the task where AutoRL is already working. How does it compare to like the RL where there's like a human in the loop, as you said earlier? Is it like significantly better, or what's like the performance difference?
So on the robot navigation task, which, I mean, the reason I'm bringing that one is because it's a real task, as opposed to like Atari or kind of one of these benchmarking algorithms. It really kind of push the state of the art significantly in the terms of how well these policies are working, and then we can put them in any environment. It was really significant difference, and then we kind of repeated that it's not in the paper, but a number of different algorithms, and then we use it for web navigation. Kind of became like one of these things you just kind of do, and not kind of think about. For real problems, reward tuning seems to be make big difference.
Thanks. So there's also a question from Manova, I believe.
Yes. Hello. Can you hear us?
Yeah.
Yes.
You said something a couple of slides back when you talked about, I think, DQN, regularized DQN or something like that. I don't know the name. You showed a table that showed that it outperforms certain state-of-the-art algorithms.
Sorry.
Yes. Does it also outperform, or does it also achieve good results on Montezuma's revenge, or is it not working on that?
Does it work where?
Montezuma's revenge.
We did not try it. We did not try it.
Okay.
But the algorithm is open source, so by all means, go ahead. It's literally like one line of change.
And since you talked about reward shaping and all of that, like intrinsic rewards, would that in theory also be possible to combine that with this approach here?
Absolutely could. And then if you're going to do that, we haven't done it. It's actually a good thing to try, because we did find that the reward search is dependent on the loss function. So you want to do first, basically hyperparameters, you want to get to the right range. So as long as you kind of have a good hyperparameters, you're fine. So then start the algorithm, pick the algorithm so you can try to do DQN regularized, and then learn the rewards that kind of fit that loss function. And then once you have that, we've also done beyond that, doing the third step, fitting the neural network architecture into the reward and and that kind of brings another layer of it. This was just as simple as how big and how deep and how wide the network is. That kind of helps, and then the hyperparameters just kind of adds a little bit more. But it'll be interesting to kind of try with the learned algorithm. We haven't done that.
Yes.
It would be even cooler to do it in a single loop, so you kind of have everything. That's probably a few years out.
Perfect. Frank?
Yeah, thanks for the nice talk. I have a related question. You mentioned some work on reward learning, and you said on the slide, like, well, learn the reward, not the hyperparameters. But then you also showed the codependence of that and the choice of algorithm. There's probably also codependence between the reward and the hyperparameters of the algorithm,
Yep.
right?
Yeah. The reason it's kind of one of
there's more playground, right? But what are your thoughts? Do you think that would be interesting to look at, and just an expensive optimization problem, or anything in the way?
aside from being expensive optimization problem, nothing else in the way. I think it's a paramount to look into the combined hyperparameter and the reward. The more we can kind of get them in a single optimization, I think the better, because it solves the codependencies.
And then to tackle that cost of that optimization, what are your thoughts on how we can get there? And so for NAS, of course, you've looked at darts. That would be tricky for reward optimization and hyperparameter optimization and so on. Yeah, well, what's the best thing you would have right now? Would it be regularized evolution with hurdle environments, or?
Regularized evolution, definitely not, because of the size of the search space and so on, especially if we add, like if we talk potentially reinforcement learning, the reward and the neural network architecture together, that kind of brings it to too big of a space. One possible way is to kind of put everything differentiable and do optimization problems. So if the reward is differentiable, which there is no reason why it shouldn't be, and NAS is formulated as differential problem as well, potentially loss function can as well, then optimizer can be possibly a tractable way. Some gradient descent and so on that will kind of capture the codependencies that we don't know about without having to know about, because that's a caveat, right?
Yeah, gradient descent. So in NAS, often gradient descent with one-shot model is not super robust. So that didn't hit you yet, apparently, for RL. But so yeah, maybe that issue just doesn't arise there. That would be awesome. Or maybe some methods from NAS that tackle that issue would make your results yet better, right?
So that's actually a good point, and it would be interesting to reward is fairly simple to learn. So maybe the way I'm thinking out loud here, so if anybody kind of has ideas, go ahead. Is if there are robust NAS methods that work outside of RL, tucking along reward and maybe loss function, maybe not, along the way with the NAS, because that's really where the big search space is, might be a way to go to combine many different things under one umbrella. And then do this kind of really larger optimization.
How about learning the algorithm, like the regularized DQN? Can you think of doing that in a gradient-based fashion?
Possibly. One thing that we did find going from DQN to actor-critic, that actor-critic space is much larger, and the generalization beyond domains might not be, I want to say not possible, rather we were not able to do it. So doing differentiable loss functions might make sense to do, because the graph representation explodes very quickly.
And so you just mentioned this generalization across domains. Is that actually somewhere in the objective function? And that was my final question.
So the if you're going to learn loss function, again, it comes down to the economics of the training. If we're going to come up with the new loss functions, where can I use that loss function, right? If I'm using a customized or kind of investing a whole bunch of time to come up with a loss function that's custom to my domain, well, that domain better be very important, or that loss function might be very generalizable. And RL is kind of currently struggling between the two. What is a really big problem to solve that we can kind of really invest lots of time in customized loss functions versus generalization across domains? And this is more of the RL problem, domain space, than the method space.
Thank you very much. So that concludes the last lecture. Thanks to the speaker again. And thank you very much for standing up so early.
That means they graduated, right?
Yeah, sure. Definitely. Good. Then we go on directly with the closing session. I hope that you have 10 more minutes. Bye-bye, Aleksandra. Good. Thank you. Good. So that's our group picture. I guess within the next hour also on Twitter, after we had already the very awesome posing picture from the winning team on Twitter. So I hope that you really enjoyed that week, that you learned quite a bit about AutoML, that you will now go into the world again and have your knowledge, have a lot of awesome tools to purchase, research ideas, and so on. Of course, all of that was only possible because we had many awesome on-site ninjas. I think I call now everyone a ninja. So we have seen Lina already earlier today, but I would also like to ask Rhea, Nia, Troy, and Andre to come to the front. So besides Lina doing all of stuff, these three were actually the guys doing a lot of stuff also before and on-site and so on, sitting here, preparing food and everything. So I'd like to thank also you three. There's a bottle of wine. If you don't like wine, then maybe you should negotiate later on whether you can exchange it for chocolate or so.
Thank you.
So thank you very much. So what's next? Of course, AutoML will not stop here. Also, AutoML events will not stop today. For example, there will be the 6th meta-learning workshop at the NeurIPS, December 2nd and or 3rd. I'm not sure about from the website. So that's at NeurIPS, but I think it's a hybrid workshop. Frank is one of the organizers. If you'd like to know more about that, of course, you can ask him. We also have a COSIA workshop. COSIA stands for Configuration and Selection of Algorithms. Of course, automated machine learning is an essential part of that. It will be in March from the 6th to 8th, actually in Paris, organized by Carola, sitting at the back. So the nice thing about the COSIA workshop, that's a workshop for free. You don't need papers, you don't need registration fees. You only have to come and discuss with that for 2.5 days or so about your ideas, your insights, whatever you would like to learn there, right? It's really like an interactive workshop. It's not like a lot of talks, but really like talking with people. So one of my favorite workshops, definitely each year. Of course, there will be also the second automated machine learning conference. Be guessing that the paper letter will be somewhere around beginning of April next year, and the conference then in summer 2023, so next year, most likely in Berlin. We still try to figure out the correct venue there, which really is also doable for us. But you can, of course, then find all the updates very soon on Twitter or on our website. Good. So, but what is missing on that slide? Of course, the next AutoML for School. That wasn't the last one. We will continue with that. We believe it's a successful format. As far as I talked with some of you, you liked that this week. We also have the next one in Munich, actually, organized by Bernd. Bernd can't be here right now because he has a very important committee meeting right now. But it will be at the MCML, and as Bernd told me, that's the best machine learning center in entire Germany. So that has to be an awesome place. Anyway, Munich is an awesome place, I believe. So I hope that maybe I can see some of you. Maybe Team 42 is winning again the hackathon. Who knows? So winning last year, winning this year, maybe winning next year. Yes, so maybe I see some of you again next year in Munich. But there's one very essential thing that also next year will be successful, that we need some feedback from you. That we know what was going well, what you really liked, what we should continue with, and maybe you're thinking, yeah, that was maybe not the most optimal way, and then you have maybe some ideas how to improve stuff further. Therefore, we have a Google form, actually. I also posted that 5 minutes ago on the Slack channel. So you would do me a real favor if you would do it simply now, right? Because I definitely now, if I'm asking you to do it next week, it will not happen. So maybe spend now 10 minutes, a few questions about what you like, what you have not liked, and then that would be all for today, actually. Because my very last slide after that is only one slide is saying thank you, and I hope I see you again at one of the workshops, maybe it's next for school, or in whatever format in the future.
One thing before we say goodbye, if any of you would like to volunteer to help out with the organization of the AutoML conference in Berlin, for example, with local arrangements or anything else, website chair, things like that, please come see me. We need all hands we can get. And it's also an amazing opportunity to get in touch with a lot of people in the community and network and so on. So thank you all for being here, for sticking it out to the end. And yeah, hope to see you soon again. Thanks.